All right, let's go. Quick, everything works. All right, cool. So we're gonna have a bit of an introduction, but first of all, we're gonna be talking about CDC, how you can basically create events where none maybe exist in your domain. We're gonna talk about strategies for how you can do that easily, and then how you can operate on those events in a logical, repeatable fashion. So this is a talk we presented at Latency. Was it 2025? It was earlier this year, right? And we're literally going to give you the same presentation beat for beat. Right, so what are we going to talk about? We're going to have an introduction. We're going to go through what change data capture is and why it matters. We're going to talk about some tool selection options, how to process and query a stream, and then finally some more complex stream processing concepts. So let's talk about our little scenario here. We're going to present Bali Bohos. This is the ultimate in Australian holiday couture. It's your typical e-commerce site. People can find gear that they love. Hopefully they can add it to their cart. All goes well, they can check out and then give us their money in the process. So here we've got a bespoke e-commerce site. So Next.js for a front-end app, API Gateway, Lambda for the back-end APIs, and Aurora and S3 for persistence. So nothing revolutionary. You've probably seen this architecture 1,000 times. App interfaces with an inventory and accounting application. Think Xero, for example, something similar. And we're selling stuff to both retail customers. These are the people that are hitting up our website, right, trying to buy like the next Bintang top, while we have internal sales teams that sell to affiliates. So these are businesses that on-sell our products. Again, this is pretty commerce-y. This is a pretty common e-commerce scenario. And while we're selling our merch through multiple channels, we have a purchasing team that's keeping an eye on our stock levels. And they work with our wholesalers to make sure we avoid running out of stock. And we're currently running a daily job that pushes information about our customers' orders to our inventory system. And this kind of presents a bit of an obvious challenge. We've got a 24-hour delay, which means our inventory's stock levels are always out of date. So a burst of sales from like a newly onboarded reseller or a spike in demand for a hot item means a lot of customers probably aren't going to get their orders in a timely fashion, or worse, they might not get their order at all. So we're going to give our marketing team a daily extract of our orders. And that means the marketing and the CRM tools they aren't constantly out of date, so missing opportunities for automation. We're also not sending out promotional codes to push sales over the line, think vouchers or discounts. And we can't really see what customers are doing with their carts. Are certain items being taken out of the shopping cart or not? Who knows? We don't have any of that information. And our database is now what we lovingly call a fragile monolith. So all of our analytics, queries, data extracts, data syncs, new features, they put pressure on our single production database, which in turn causes our front end to become less and less responsive. This also contributes to higher compute costs, which leads to some really unpleasantly large bills. So we were talking about CDC earlier. Let's come back to this concept and let's talk about what CDC is. How can CDC help us alleviate some of the problems that we've just laid out here? And these are common problems, like I said, that you've probably seen in your line of work, even if you're not in an e-commerce sector. These scenarios come up quite often. So what does CDC stand for? CDC helps us turn database changes into real-time business events. If we can track changes that we make at a database level, then what's to stop us from capturing those changes as actual events? CDC helps us capture granular changes, individual row-level modifications as we commit them to our database. And we can do this by emitting an event that captures all of the details about a change. It also helps us enable real-time reactions, which allows downstream systems like analytics platforms, caches, microservices to respond immediately when there's an update to our data. So without waiting for like a slow batch process, that once a day job that we run or that CSV extract we create at 12 p.m. to give to our marketing team. It also avoids database strain. So efficient CDC methods, especially like log-based methods, prevent the need for downstream systems to constantly query the source database. Right? You've probably encountered this issue. I think I was running into something similar today. And this reduces the performance impact. It also decouples systems. So the source database doesn't need to know about the systems consuming the changes, and consumers don't need direct access to the source database tables. and it provides rich context. So change events typically include metadata like the type of operation, it's an insert, an update, a delete, timestamps, and very often, most notably, the change data, what actually changed. So let's talk about our application architecture briefly. Marcia here accesses our e-commerce site using their favorite web client, which issues a request to our API gateway that uses Lambdas to interact with AuroraDB. And here's the ERD for our database. You don't have to memorize this. Pay close attention to the orders and products. We've got a join between these two tables. That's the order product table here. And in this example, we're using AWS DMS to track changes in our Aurora database. DMS monitors row-level changes in our database and emits a CDC event, a change data capture event, as a result of that change. And this is the first step in breaking out of that toxic integration pattern that we saw earlier. You still remember that nasty CSV file export and the daily sync job that we talked about earlier? This is a way to break out of having to do that. So let's look at a more detailed example. Our journey starts with a user adding an item to their cart. Here's the resulting API call. And the application backend receives the API request and translates it to a series of SQL statements that modify the data directly within the source Postgres table. And here we're inserting a new row into the order product table and updating our stock level accordingly. DMS detects both of these changes, and it emits a CDC event that describes the insertion of a new row into our order product table and a CDC event describing the change in stock levels for the item that we just sold. So hopefully everyone can see that. All right. So why bother with CDC? First, it gives us faster time to value. So we can access and stream real-time data changes in weeks or months, not years that it would take for us to do an application rebuild, not to mention the nightmarish migration we'd have to do if we rebuilt our entire app. It's cheaper, so we can avoid massive investment in rewriting entire applications. Instead, we can focus our effort on data integration and consumption. It's less disruptive. So it's always best to minimize the impact on stable operational legacy systems. You really want to be careful around them. Log-based CDC reads changes non-intrusively, and it avoids risky modifications to legacy application code. It also allows us to take a slow burn approach to modernizing our applications. So we build new event-driven features, real-time analytics, microservices that use the data streams from our legacy systems. And this allows gradual evolution rather than a big bang replacement of legacy apps, which still scares me. So, and last but not least, it helps us make use of our data now. So with CDC, we can make critical data that's locked away in older systems, that's difficult to access, readily available to cloud platforms, data lakes, downstream applications, without complex source code changes to our legacy applications. So let's talk about the various approaches we can take to realize the CDC pattern, and let's start with Amazon DMS. So how does it work? It uses the underlying database transaction log and supports a wide range of databases, supports Postgres, MySQL, Oracle, SQL Server, you name it. DMS handles the setup, patching, and scaling of the underlying replication instances. And it can actually integrate with a wide range of AWS services, think S3, Kinesis, Redshift, MSK, OpenSearch, Lambda, and many more. It can also capture changes from one database type, say Oracle, and replicate them to another, like RDS or Aurora. And the schema conversion tool can be used alongside DMS to help migrate schemas, especially between different database engines. So DMS task defines the end-to-end behavior of data migration or replication job. A task has three core components. So a source endpoint, that's the origin DB. A target endpoint, that's the destination database. And the migration settings. So these define the type of migration required and how it should be carried out. So there are three types of migrations we can carry out. Full load migration migrates the existing data once. CDC only captures ongoing changes, inserts, updates, and deletes. Full load in CDC first copies all of our existing data and then switches over to CDC. So let's take a look at DMS rules next. So these allow us to define the changes that we're actually interested in tracking. So not every change that happens is something we want to know about, right? So selection rules are mandatory. Without them, DMS won't know which tables to process. So here we've defined a rule called include product table. It includes the product table, unsurprisingly, from the e-commerce schema. And next, we're going to jump and take a look at DynamoDB. Sorry, I'm jumping around a bit. We will come back and talk about some of these concepts in a bit more detail, but I want to give you a broad overview first. So while it doesn't have DMS-style rules, it does have native support for CDC by virtue of a feature called DynamoDB Streams. So this gives us native integration with DynamoDB. It allows us to capture a time-ordered sequence of item-level changes in a DynamoDB table. So with DynamoDB Streams, we're fully managed and serverless. There's no infrastructure to provision. There's nothing for you to manage other than the stream itself. Changes appear in a stream within seconds of happening in a table. And we're guaranteed the sequence of events for any given partition key. And we can configure the event payload. And we'll take a look at this shortly. So it's very common to trigger AWS Lambda functions directly from the stream for event processing. DynamoDB Streams makes this very easy with seamless Lambda integration. Now let's take a closer look at how we can use the stream view type parameter to control what's actually included in our published change events. The most critical choice determines the content of our change event records. And the options are keys only. This captures the keys of the modified items. So this is minimal in size, low detail. It's just the keys and nothing else. New image captures the full item after the change. So this is really useful for replication or updates. Old image captures the item before the change. So think of auditing or deltas, right? New and old images, creatively named, gives us both of the states. So this is the highest resolution possible, but obviously the largest in size. You've got the before and the after. Consequently, this makes for really easy delta calculations. Everything you need is there in hand. The choice you make affects the event size, the consumer read costs, and the data available when you're processing the actual event stream. So the less you put in the change events, the less you'll have when you're processing the stream. So when do we use keys only? So if you primarily need to know that an item changed, but not necessarily the details of what changed, this is basically perfect for you, right? Let's look at some use cases. So for simple cache invalidation, this is great. You want to send a signal that invalidates a cache entry based on the primary key. This is your go-to. The next request here can just fetch the data directly from DynamoDB. We don't need to keep that information in the actual event. Or we can trigger a generic notification or a downstream workflow if an item is being inserted, modified, or deleted. For example, order UUID 456 was updated. Or maybe to kick off a process that needs to know an item was created or deleted, right? So to potentially we can manage related resources or counters somewhere else in our ecosystem. And finally, penny pinching. So when an event size and read costs are your primary concerns, you want to minimize your costs, and you're willing to do a follow-up get item call on a need-to-know basis, this is great. So you only go and fetch if you need to, and you can save costs this way. So next up, let's look at the new image option. If you want a complete state of the item after the change, you want it to be available directly in the change event, this is the option you want to use. We can look at some use cases. This is useful if you're copying the current state of items to another system, like a data warehouse, like Redshift, or a search index like OpenSearch, or another DynamoDB table. Or you're keeping aggregated views of some other data or data structures up to date based on the latest information. Again, this is very useful. Or you're sending the most recent item data to display to users. If you need to ensure the search service has a current indexable content of items on hand, again, this is very useful. Finally, you can have, if you have an aversion to making get item calls, you want to avoid hitting your database to request details. Maybe your consumers almost always need the full state of the item anytime there's a change. This is your go-to. And now onto old image. So you want to use this setting if your focus is understanding the state of the item before it was changed or deleted. So this is not available, obviously, for insert events because there was no item. You're inserting it for the first time. And some use cases, logging the state of an item before it was modified or removed. This is good for compliance or historical tracking. When an item is deleted, you may want to use the information from its previous state to clean up, say, associated external resources. So, oh my God. Sorry. I don't know what I did there. Okay, I'm back. Okay, maybe less twitchy on this. All right. So you may need the items S3 object key, obviously, to clean it up, to clean up a bucket, for example. This is, again, a useful thing to have. So if you have a previous state and you're able to fetch the current state separately to compute the difference, again, not a bad strategy. And finally, having a prior state might help you in designing logic to revert changes, although this can be a little bit tricky and isn't as easy as it sounds. And finally, maybe you like to have your cake and eat it too. You can have new and old images, as we mentioned earlier, but seriously, when do you need to go down this route? You take this road if you need the most context directly within the event stream. So you need the before, you need the after. This gives you both of those bits of information. Use cases to send it home, great for recording exactly what changed. Field X went from value A to value B. Or you want to compare the new and old image within consumer logic without needing to go to the database and retrieve the item in its current state. Again, so here, we have no need to actually do an extra call to work out that stock decreased by 5, right? And maybe triggering different actions based on how the data changed. So for example, if order status changed from pending to shipped. And it's also helpful when downstream systems need both states to perform transactions or handle conflicts. And this probably goes without saying, but having both states is invaluable for understanding how data is changing over time. So you've got everything you need in the event stream. And as to be said, this approach provides maximum detail, but results in obviously the largest event sizes of all of the 3 options, and potentially higher stream read costs. And there's some important considerations if you do choose DynamoDB streams. Filtering and routing, they're handled exclusively by your consumers. There's no built-in stream filtering. Consumers, like Lambda, for example, they're going to have to filter events based on the content only after reading them. So there's no built-in routing. Consumers have to target a specific ARN for the stream. And subsequent routing to different destinations requires logic within your consumers. So for consumer integration, it's recommended you use Lambda. You'll need to configure Lambda triggers. Think batch size, concurrent batches per shard, retry attempts, max record age, dead letter queue for error handling. All of this stuff is on you. An alternative, obviously, is the Kinesis client library, KCL. And for this, you need to manage consumer application specific configuration. So there are some inherent behaviors you need to take note of. Events are only retained for 24 hours. Strict event ordering is guaranteed only for changes within the same partition key. We mentioned this earlier. And to make the right choice, you have to ask yourself these 3 questions. What's your source? Where's your target? And how much flexibility do you need? And who manages the infrastructure, if you're going to sneak another question in there. So let's do a quick recap of all of our options. AWS DMS, solid choice when you're migrating data into AWS. Especially from relational sources like RDS or Oracle. It supports full load and CDC, and it integrates well with S3, Kinesis, Redshift, you name it. You don't get deep data transformation capabilities, but filtering and some remapping is possible. So being a managed service, it handles a lot of the heavy lifting for you, but it's not serverless. You run and pay for a DMS instance. So DynamoDB Streams is your go-to if your source is DynamoDB, which makes sense. It's fully managed, it's serverless. That's ideal for triggering Lambda functions on data changes. The format is fixed based on your stream view type, which we covered earlier. So there's limited transformation flexibility, but it's incredibly simple to use. It's cost effective for real-time event-driven workflows within the AWS ecosystem. So as we've seen, CDC turns your low-level data operations into events like this event that tells us we've inserted a new row into our order product table. Basically, our customer has added a product to their order, or this event about an update to the stock levels for a specific item in the product table. In this case, we've sold 2 units. So maybe let's talk a little bit about why we want to process streams. For that, Ben, do you want to take over?
Thanks, Rami. So has anyone here actually processed streams before? Yeah, fair few. Does anyone enjoy it? Yeah, it's pretty... It takes a while to get your head around it, so hopefully I can provide some insights here. So say you want an event that contains the information about an entire order, and not just one about the product being added to the order. Or only wanted to see events that showed a change in a product stock levels, ignoring other attributes like the price of a product. or maybe an event that we've sold 100 units of at the same time. So how do we query these events? They'll need to be published to a streaming solution like Kinesis or Kafka, and we'll need to convert the events from simple deltas, like this one here, to meaningful business events. So why should we bother transforming our streams into business events? For one, querying streams is quite difficult, so it's easier to consume these topics from queues and SNS topics and the like, or EventBridge, rather than having to write the SQL to query the stream. And business events naturally represent domain events or a particular state to call us to an action. And it's a good idea to decouple ourselves from the low-level change data capture mechanism. I don't want some SQL, Flink SQL in the middle of my code somewhere. I want to decouple it out, publish a business event to consume. So we'll pump our deltas or change events into a Kinesis stream, then transform these changes into business events and publish them to the relevant topic. And then finally integrate these events with downstream systems like our finance and inventory platform. So with Kinesis, we get a stream of change events, and we can transform our raw deltas into meaningful business events, like in our previous example where we transformed the change to the base stock level for an item in the product table into a stock level change business event that we feed into our inventory management system. And then we can query our business events. For that, we've got a few options. First off, one that I really like, Lambda. Lambda integration with Kinesis is achieved by event source mapping. So this is official AWS supported, and it allows us to trigger the Lambda to process records from a Kinesis data stream. And we don't need to write any polling code. So those of you who didn't start in the cloud with serverless functions, you probably remember you have to wrap the whole thing around, loop, poll, are there any messages, loop back around. You don't have to do any of that with Lambda if you integrate with Kinesis, so great time saver. And all of our processing logic is continued within the Lambda function. So this receives batches of Kinesis records and decodes these into JSON, then performs filtering, mapping, enrichment, all that good stuff, and applies any relevant business rules. So we get this business event, we might want to perform an action, add it to our finance system, notify someone. And when it comes to Lambda, there are some common use cases. So think stateless transformations like field renaming, simple filtering, lightweight enrichment requiring calls to other AWS services, triggering downstream notifications or workflows based on specific changes, a basic stateful processing when using an external store like DynamoDB. You'll need to pay attention that you will need external persistence to managing any complex state across invocations, and there's a maximum of 15 minutes of execution time, as I'm sure lots of you know. And also watch out for the cold starts when it comes to improvement events. So let's take a look at this example here. Do not run this code. Please do not run it. It is overly simplified and does not have a lot of error handling in it, but it shows you what one of these lambdas might look like. So we're looping through each record that we receive from the Kinesis data stream. Each record contains a base 64 encoded DMS change event. We extract these, decode them, and pass the JSON to extract the metadata. This is for info like the table name, operation type, etc. And then the data, the actual row of the database that has changed. And now we do some filtering. We only proceed if it's a data change event, not a schema or control event. Table name matches product. The operation is insert or update, and the data payload is present. Now we then go on to extract the SKU and stock level from the events data row. And finally, we call a function that is not shown here because I've run out of room on this slide to publish this structured message to an SNS topic. So this can notify other systems and trigger some downstream processing, business events, business process, whatever. And your second option, if you don't want to do Lambda, you can do Kinesis analytics. So for integration, Kinesis data analytics applications is SQL-like. So similar to Apache Flink if you've ever used that. And it can read from one or more Kinesis data streams. And as far as the process logic goes, for a standard stream analysis, we can use a SQL-like interface, and our processing runs continually in a fully managed environment. So here we have a customer placing a new order, and then the customer adds an item to their order, and another item is added to the same order. And what we want to do is create 2 business events, one for each item, joining the information about each product that is added to the order with the details of the customer that placed that order. Because we don't want our business events to just have the order of the product in the order. We want to have this extra information like the customer ID and that. So this gives us business events for each item ordered, enriched with the customer's details. And this is what the SQL looks like for Kinesis data analytics. So it's fairly similar, a few unique things there, but you'll get the idea of it. Notably, the window at the bottom is where a lot of people start to have troubles. So a pump in Kinesis SQL pushes data into a target stream or table, and this creates or replaces a pump that inserts enriched records into the enriched order line's output stream. The main select statement extracts order line information, OP, and joins it with the order header info, O, like customer ID and order status. Finally, we have the window join with the order stream. We perform a left join to include all order line records, even if a match in the order stream isn't found. And the join is done over a time-based window. Here we create a 1-hour sliding window that groups order header records by order ID and considers only those that arrive in the last hour. This helps us match events that may arrive slightly different times. Because you can imagine the customer's information might update, but when they add that item to the cart, we want the state of the customer at the time when they added it to the cart, not 20 minutes before or 4 hours later. So streams aren't a silver bullet. There's some challenges. In a stream, events never stop. So how do you group these together in a meaningful way? So this is where that windowing comes in. We can use windows to define time-based boundaries around events, and different windows helps us solve different kinds of problems. So first we have fixed or tumbling windows, and these are good for clean hourly summaries, think your dashboards. Sliding windows, they're really good for detecting trends and changes that evolve over time. And finally, session windows, they're good for capturing human behavior like browsing, shopping sessions. Basically, someone finishes their cart, they close their browser, we want that to be the window. So it's these windows which give the underlying stream processing engine a manageable, logical chunk of data to work with. So we'll start with an example of a fixed or tumbling window size of 10 minutes. Each interval on our timeline is 5 minutes long, so a 10-minute window sits nearly over 2 blocks, yep. Our first window contains 3 orders worth $4, $2, and $8. This gives us a total of $14 in that first window. Sliding the window across to the next 10-minute interval, we find just a single order worth $1. So without that final window, with the final window, including a single order worth $9 there. So next we'll look at how a sliding window works. They're slightly differently, so they don't jump by a discrete amount of time. It continuously moves across the stream, say every second or every time we receive a new event, depending on what stream processing service you're using. This makes perfect for any sort of analytics task, like triggering an alarm when the total number of orders in the past 10 minutes falls below 3. So we'll take a look at this one. So if we slide our 10-minute window along by 5 minutes, we see that we've had a total of 3 orders in the 10-minute window. And pay attention to the fact that we've included the 2 orders from the last window. as well as the current one. Slide in the window another 5 minutes, we find the total number of orders is, last 10 minutes is 2, and an alarm is now triggered as there were less than 3 orders in the past 10 minutes. So let's consider the difference between event times and processing times, because we might get some late arriving data. So starting with event times, they represent when a business event actually occurred at the source. These times are usually embedded within the event data, say the database transaction commit time, application log timestamp, IoT sense and reading time, and they represent a historical fact about the event itself. As for processing time, well, that's when it's recorded in the event stream. So it's when it observes or handles the event in the stream. So they're generated by the processing engine's clock in the stream engine. And these times are variable and they're influenced by ingestion latency, network delays, queuing, system load, clock skew. You can imagine you get a million messages within an hour. It's going to start to slow down and you're going to get a large difference between that event time and the time it hits the stream. So we've got a problem to solve. What happens when they come in late? Without handling this, we will misplace events or miscount them. So this is where we introduce the concept of a watermark. So here's a scenario. Say we have an event representing a financial transaction. To get an end of day report, we want to use the event time over the processing time, as finance doesn't really care when it's processed, they want to know when it actually happened. Accurate event timing affects business decisions like dynamic pricing, inventory restocking. A customer might place an order, then cancel an order. These events might be processed out of sequence. We don't want to restock an item if it's out of sequence, so if our event arrives, thinks processed, then later the exact time it occurred, then it won't make the cutoff for the end of day financial report. So let's see how we can solve this problem using a technique called watermarking. So say we wanted to take all the events between 0 past and 5 past. An event won't be processed if it arrives outside of our processing window. So now here's a part of the stream that scares me. It's the watermarks. So think of a watermark as the stream processing engine's best guess about data completeness based on event time. It's a bit like this. So based on the event times I've seen so far, allowing for some delay, I believe I've received all events that have occurred up to event time T. So we look at the previous stream, we say, all right, I'm starting to see events from like 1 a.m. now. I'm pretty sure I can trust that everything from midnight's already been processed. So that's how watermarks work. So it lets the streaming engine decide when it's safe to close a window, with later events that arrive before the watermark still being processed. The late events after the watermark may be discarded or flagged as late. You will probably want to get notified of these as it can get nasty. But every single system that deals with streams is going to have events. Well, probably it's unlikely they'll get events that miss the watermark, but you need to be able to handle them somehow. So let's hurt ourselves by looking at an example of this, and I'll try to explain it. So first off, I want to note that the processing time progresses in an orderly fashion, but some of our events are arriving out of order, like this one and that one there. So simple watermarking strategy progresses the watermark by a fixed time every 5 minutes. So this is a very simple watermarking strategy. So we're not looking at previous events to determine our watermark time. We're just forcing it, saying, hey, if 5 minutes have passed, I can sort of trust that the events arrive in from 5 minutes ago. That's all. So say I want the total of all orders between 0 minutes past and 5 minutes past. We'll look at all the events that were produced between the processing time of 0 past the watermark to 5 past. So we select all the events up to the watermark. So you see that those events have arrived past 5 past, but they're still going to the watermark, and filter any events that actually don't fall within the time frame we're interested in, giving us a total of $6 worth of orders. Be careful when selecting your watermarking strategy, as dealing with late arriving events is very tricky, and most people just try not to think about it when they go to sleep. It's all like when you generate UIDs. It's like, technically you could get 2 that are identical, but I don't want to think about that. So here we're interested in events that occurred 10 past and 15 past, which leads us to, which includes this event, but leaving out its very late arrival, typically leading either a manual process or a complex automated task, you have to deal with that. So do really think about your watermarking strategy, because you don't want that. So let's wrap it up. CDC acts as a bridge between operational databases and real-time analytics. It supports better business decisions with immediate data insights. It helps us avoid information loss. Your tool choice impacts ease, scalability, and maintenance. Seriously, use the managed cloud services. Scaling streams is a pain. Stream processing with Kinesis Windows watermarks ensures reliable, accurate analytics. And look, if you had one shot, one opportunity, would you seize everything you ever wanted? Would you just capture it or let it slip? And now we're on the Q&A with the very, I mean, Trump's still relevant, so it's, our meme's sort of held up from 3 months ago. We need a few of Elon Musk. Yeah.
Apologies. I think that's it.
Yeah, that's Q&A.